All right, let's get started with section 8.3, proving triangles similar by the side-side-side similarity and the side-angle-side similarity theorems. So our objectives are to use the side-side-side similarity theorem, use the side-angle-side similarity theorem, and prove slope criteria using similar triangles. So our essential question, what are two ways to use corresponding sides of two triangles to determine that the triangles are similar? So let's get started with our first theorem, the side-side-side similarity theorem, located on page 440 of your textbook. It states that if corresponding side lengths of two triangles are proportional, then the triangles are similar. And I've bolded and underlined keywords within the theorem. You need all three pairs of sides to be proportional in order for you to then conclude that the triangles are similar. But if all three pairs of sides are proportional, then you can definitely conclude the triangles are similar. So we see here with this example, triangle ABC compared to triangle RST. And for now, there's no links given on our picture. So this is just a general summary of our conditional statement that states that if the length of AB compared to the length of RS is equal to the length of BC compared to ST's length, which is equal to the length of CA compared to the length of TR, if all of those comparisons are equal, then we can conclude that triangle ABC is similar to triangle RST. All right, so let's check out our first example and answer the question, is either triangle DEF or triangle GHJ similar to triangle ABC? So we're going to compare these two triangles to this first triangle. And I have all the side lengths in particular colors. They are in the color arrangement based on their lengths. So if we notice, all the red side lengths are the shortest lengths within each triangle. And then the blue lengths appear to be the longest side lengths between each of the triangles. So this is really important because that's how you want to sort of plan out how to set up your proportion. So this is exactly how we will plan setting up our proportions. When we're using the side-side-side similarity theorem, you definitely want to compare your shortest sides and your longest sides, and then whatever's remaining gets compared as well. So that's exactly the list that we'll make, and we'll start by comparing triangle ABC to triangle DEF. So for the shortest sides, I have length AB divided by length of DE. And because I have them both color-coded for red, shortest side lengths, I have 8 divided by 6 simplified to 4/3. Next, I will compare my longest sides. So that's length of AC compared to length of DF. Substitute the numbers, or the side lengths, so 16 and 12, which reduces to 4/3. So far, my shortest side and my longest sides have the same proportion. But I must compare the remaining sides. I need all three pairs of sides. All right, so then my remaining sides, BC compared to EF. So 12 compared to 9, reduced to 4/3. So I have 4/3 ratio throughout all of my comparisons. So in conclusion, so triangle ABC is similar to triangle DEF. All right, next let's compare triangle ABC to triangle JHJ. So I start with my shortest sides, so that's 8 and 8, and that reduces to 1. Then when I compare my longest sides, I have a 6:5 ratio when it's simplified. So that means I can conclude that these two triangles are not similar. My ratios do not match. And there's no reason to continue to get the third remaining side lengths compared, although it would be good practice to do it just to follow through, just to make sure you haven't made any mistakes. If not, you can conclude that the two triangles are not similar if the ratios are not equal. All right, in our second example, we're going to find the value of x that makes triangle ABC similar to triangle DEF. So what we want to do is match up, again, our shortest side lengths and our longest side lengths. We can also look at our similarity statement and decide how to match up sides as well. So AB is first and DE is first, so therefore they are corresponding side lengths. BC is next compared to EF, and then AC compared to DF is another way you could set them up as well. All right, so my first step for finding the value of x that makes the corresponding side lengths proportional is to set up my ratio with just the sides mentioned. So I'm comparing, like I said, AB to DE, and then comparing BC to EF, and those must be equal in order for them to be proportional. Next, I substitute all the given lengths for the sides in my proportion, resulting in 4 divided by 12 equals x minus 1 divided by 18. In order to cross multiply correctly, you want to make sure any expressions that are in the proportion are in parentheses so that you can catch yourself when you do the cross product to include the proportion with the parentheses as indicated here in our next step. So we have 12 and then parentheses x minus 1. And then on the other side, our other cross product, which is 4 times 18. And then make sure you distribute. So I'll distribute the 12 to get rid of the parentheses, so we get 12x minus 12 on one side, 4 times 18 equals 72 on the other side. Continuing to combine like terms, so we add the 12 to both sides, resulting in 12x equals 84, and then 84 divided by 12. So we add that in, so we get 84 equals 12x in between the steps here, and then divide both sides by 12, resulting in x equaling 7. It's always good practice to check your answer for x by substituting it back into the original proportion and situation just to make sure it all works out. So if we substitute 7 back into the expression x minus 1, we get 6. If we substitute 7 into the expression for df, we get 24. And then when we substitute into our various proportions, we see that we have a match of equal ratios and proportion. Therefore, our final statement, when x equals 7, the triangles are similar by the side-side-side similarity theorem. Also, we can write out our implied statement. Implied statement states that if all sides are proportional, then this implies similar triangles. All right, our next and second theorem, and this is the final theorem that we could use to prove triangles similar. We have the side angle side similarity theorem. It states that if an angle of one triangle is congruent to an angle of a second triangle, and the lengths of the sides including these angles are proportional, then the triangles are similar. Super important. So what we're stating here is, for this particular diagram, we have angle X and angle M marked as the congruent angles. So that means that the sides where the included angle occurs are the ones that must be proportional. So this angle is included between XZ and side XY. So these are the two sides that we must use in our proportion. And then angle M is included between side PM and side NM. So therefore, these are the two sides we must use in the proportion. So when we set up our proportion of those specific corresponding sides, they must be proportional, and then we can conclude that the triangles are similar. So your implied statement for this theorem is if side angle side similar will imply similar triangles. All right, so let's take a look at this real world situation. Example 3, you are building a lean-to shelter starting from a tree branch as shown. can you construct the right end so it is similar to the left end using the angle measure and lengths shown? All right, to start off thinking about our solution, we can see that the measure of angle A and the measure of angle F are both equal to 53 degrees. So that means angle A is congruent to angle F. So I've marked my picture according to that information. Next, compare the ratios of the lengths of the sides that include angle A and angle F. So that's going to be the length of, so that's going to be this side length FG compared to length of AB, and then FH compared to AC. And so we're going to take our shortest sides. We'll start with our shortest sides. So AB compared to FG, so 9 divided by 6. And then your longer sides. AC compared to FH, which is 15 over 10. Always simplify your ratios. So we simplify both ratios down to 3/2. The lengths of the sides that include angle A and F are proportional. So by the side angle side similarity theorem, we can conclude that triangle ABC is similar to triangle FGH. So the answer is yes. You can make the right end similar to the left end of the shelter. All right, and then I added in an extra example here to illustrate also a different way to think about your side angle side and how to use it. So here we have a picture of triangles that seem to be connected and intersecting at point C. So our first question, what method would you use to show the triangles are similar? To start, we can see that angle ACB is congruent to angle DCEE. And that's because they're vertical angles. So I'm going to mark my two angles that are vertical, therefore congruent. That means I'm left with two sides that include those angles. So I could possibly use the side angle side theorem. So setting up your proportions, so do the shorter sides and the longer sides. So you have your 18 and your 30. These are your longer sides. And then you compare by a 3:5 ratio when you reduce your fraction, and then compare your shorter side. And that comparison reduces down to a 3:5 ratio as well. So since I have congruent angles and I have the sides including those angles proportional, I can conclude that the two triangles are similar. So for part B, my similarity statement says triangle ABC similar to triangle DCE, and the reason is my side angle side similarity theorem, which implies similar triangles. All right, that's all for this evening's notes. Be prepared to practice problems involving these two theorems tomorrow in class, and see you then.